Bismillahirrahmanirrahim. Assalamu alaikum students. Today's lecture is about designing lead compensators, lag compensators or any kind of controllers on MATLAB. So what do we have over here is a transfer function, a problem that we need to solve. This is the transfer function that we need to set up in a unity negative feedback system and then fulfill the requirements given below, that is settling time 2 seconds and overshoot 20%. So there are two methods to solve the problem. First one is using the MATLAB one and the other one is using the paperwork and all the calculations. So in this video we'll be going towards the MATLAB one, and inshallah in the upcoming video that I'll upload inshallah very soon, I'll be doing it using the hand calculations. So you can see that we have a third order system, and without wasting any more time we'll move forward to writing its transfer function in MATLAB. We can see that we have a pole at 0, at -3 and -6, and no 0 in the system. So I write my transfer function over here, which is a is equal to zpk. As I told you, we had no 0 and a pole. We will get we'll go backward to see the poles: 0, -3 and -6. So we have 0, -3 and -6, and here I set the k value, the gain value, to 1. Okay, so I just enter it. We have the transfer function over here, that's our given transfer function. Okay, so what do we do now? I use Sisotool and open the transfer function A. Okay, so Sisotool automatically sets up the transfer function in a negative feedback system and shows up its response, step response, and the root locus. So this is the layout that you can see, that this is the transfer function that I have written, and the Sisotool has itself automatically generated a feedback system, and thus it has given me these closed loop poles that I can move with the help of this hand tool. I'll just maximize it that we can have a look at this. Okay, so you can have a look that I drag these closed loop poles and the value of loop gain changes. It's changed to now 0.001, and when I drag these boxes more forward and further, it's changed to 270. So this is basically what we are doing, that changing the value of k, and this changes the value of closed loop poles, and that's simply I'm doing by dragging the closed loop poles. Now just we need to have a look that what is this system giving at the right moment in terms of response. So I have clicked on analysis, response to step command, and now I'll see that what is the response of this system. I'll first of all remove the green line, that is R to U. I need to see R to Y. So I'll uncheck it. So you can see that the characteristics of system, that is the settling time that we require to be at 2 seconds, is at 6.5 or 7 something, and this needs to be set to 2 seconds, and the overshoot needs to be dropped down to 20%. So we'll have a look. I'll just close it down. The first and foremost thing that we need to do is right click over here, design requirements, and click on new. This is the settling time. We'll go back to the PDF. We'll see settling time is equal to 2 seconds. Okay, so I come back over here, put in 2, and I press OK. You can have a look that after I pressed OK, in the settling time requirement we have a straight line, dark straight line over here. This is representing the section of root locus, this line, exactly this line, where if closed loop poles are placed, the settling time of system will get to 2 seconds. But make sure this line is for a second order system, and we have a third order system. So whatever we will be doing is that we will be approximating our third order system to a second order one. So this is the line for settling time is equal to 2 seconds whenever the closed loop poles are dragged such in a way that they come over this line. You can see that one of the closed loop pole is exactly on the 2 seconds settling time line. This is the point where we'll have a 2 seconds settling time for a system, for a second order system. Okay, but you can see that we have a third order system, and even if we apply the second order approximation, we are only having a single pole on the settling time line. These are only one of the 3 poles. So to apply a second order approximation, we need to have at least 2 of the closed loop poles, I mean 2 of these pink boxes on this settling line. You can have a look that these cross, this cross and this cross are representing the open loop poles, and these are not movable. If I drag them, I click them, I'll show you. I'm just putting them away, and now if I click this cross, you can see it's not moving. I'm clicking it harder, but there's no response. Only these closed loop poles, the pink boxes, move and result in change of loop gain. So this is a line design requirement set to 2 seconds. Now what we need is the second thing, a overshoot of 20%. Okay, so what do we do over here is that we right click again, select design requirements, select new, and here design requirement type, we click on percentage overshoot and set it to 20%, and now I click OK. So this is what you can see, that a zeta line has appeared on the system. This line basically in the negative axis represents 20% overshoot zeta. So whenever these closed loop poles will be on this line, you can have a look that yes, over here you can see that 2 of the closed loop poles, this one and this one, don't think that these lines moved, only the view has changed because I've moved these poles. So these poles are now on the zeta lines for 20% overshoot. But what about the settling time? They are far away from the settling time line. So what do we need is that to have a 20% overshoot and a 2 seconds settling time, we need to have our closed loop poles on these intersecting points of the design requirements line. Exactly at these intersecting points we'll have a overshoot of 20% and a settling time of 2 seconds. But you can see that if I drag these poles, no matter how much I drag these poles, both of these poles never come to these points. Why? Because the root locus is not passing these intersecting lines. It's only crossing the zeta requirement, or it's crossing the settling time line over here and not the overshoot line. So what do we need to do is that we need to place zeros or poles in such a way that the root locus is altered and the root locus starts passing through these intersecting points of our design requirements. So what I do is that now we have been given in this in the problem that design a lead compensator, and you know that lead compensator has only one of the suggestions that the that the zero should be on the right side. I place it over here, and the pole should be on the left side of this zero to have a positive or a lead compensation. So what I've done is that I've placed a zero. Okay, I guess I've missed telling you that how I've placed it. So I press Ctrl Z and Ctrl Z again. So I'll show you again. I have selected this add real zero, and then on this line I have ticked, and you can see that this a pink hole has appeared, and by moving this zero our root locus is changing. You can see that. Okay, so this root locus is changing because I have placed a zero, and this is a movable zero, but this is not a movable pole. This is a movable zero because this is a new zero to the system and I can drag it according to my choice. Now because we need a lead compensator, so I'll place a pole, add real pole, and you can see the cross mark with the mouse. It says that wherever I will click, it will place the pole over there, and I place the pole right left to the zero I have placed. So now I have placed a zero and a pole. Now what I need to do is I need to drag this 0 and pole in such a way that root locus starts passing this intersecting point. Okay, so I start by dragging the pole, and you can have a look that the root locus is changing its position. Okay, so now we have changed the position, but still it's not passing. I'll just zoom it so that you can have a better look. Okay, so now what I'll do is that I'll click on the mouse hand tool back, and now I'll drag this 0 in such a way that our requirement, you can see that I'm checking both the ways that the root locus changes in such a way that it starts passing the intersecting line. Okay, I guess we are here. Okay, and I'll zoom it out further to have a better look. You can see the root locus is now clearly passing the intersecting point. I'll just make a little more addition so that it passes exactly through the intersecting point. Okay, so I guess we are done. It's clearly passing the intersection point. I'll just zoom out. So this is the root locus now, and it's passing the intersection points. What's needed to be done now? Don't forget this thing, that we need to drag the closed loop poles to the point where the design requirements are now intersecting. And you can have a look that by dragging these poles, the other two poles are also being dragged, and here we have on the intersection points, the closed loop poles are now located on the intersection points. I'll zoom it out for you, and you can have a look. This closed loop pole and this closed loop pole is right on the intersection point of the design requirements. Now of this system, we will perform analysis response to step command. Let's hope for the best, because I guess we have done exactly to the requirements. And what we'll do is, you can have a look that we have this step response over here, and I'll click on the characteristics and the peak response. Here the overshoot of this new system is 17.5%. okay, woohoo. And this settling time is 1.99 seconds. So basically what we needed was a settling time of 2 seconds and an overshoot of 20%, and we are achieving an overshoot of 17.5%, which is a more better thing to have, a lesser overshoot than the design requirement. So basically, why this change? Actually, that you might be thinking that we have exactly placed the poles on 2 seconds and 20% overshoot, then why this 17.5? This is because of the second order approximation. I need to show you this. There are two poles, two closed loop poles on the design requirements, but other than them, there are two other closed loop poles in the system also, which because we have placed a pole and a 0, which making the system a fourth order system and having 4 closed loop poles, and only 2 of the closed loop poles are on the design requirements. So basically the thing is that we are only applying a second order approximation. This is a second order approximation line, this settling time and this zeta line. Now only the thing that needs to be done is that we need to have a look that what is the value of gain k and what is the transfer function that we need to add to our system. So I'll click on design and then edit compensator, and you can have a look that compensator C is giving me some values, 60.785 and 1 plus 0.36s and 1 plus 0.086s. So this is the compensator transfer function that we are going to add to our system, but make sure that you perform an extra calculation too. You can see that this is 1 plus 0.36, but normally we have our poles in this form, s plus 3 and s plus 6. So what do we need to do over here is that we need to find the final transfer function. Okay, so we have a 60.785 compensator k value, but here we are having a pole, a 0 at 1 plus 0.36 and a pole at 1 point 0.086. We know that the real 0 is at minus 2.81 and the real pole that we have added is at minus 11.6. okay, so what I'll do is that I'll take out 0.36 common from this system, and you know that if I take out 0.36 common from the numerator, it will become s plus 0.31 divided by 0.36, and if I take out 0.086 common out from here, it will become s plus 1 divided by 0.086. okay, so that would be if 1 is divided by 0.36, you can have a look and you can have a check that it would be equal to minus 2.81, and if 1 is divided by 0.086, you will see that the real pole value minus 11.6 will appear over here. But what about the terms that have came out common from here, the 0.36 and 0.086 term, that the terms that we have taken out common from the numerator and denominator, we need to multiply them, divide them to add to the compensator value, the gain k value that we have over here. So what we need to do is that we will multiply 0.36 divided by 0.086 to the 60.785 value, and we have a 0 at minus 2.81 and a pole at minus 11.6. so what we'll do is that we will recheck that have we done a good thing or no. So I'll change the zpk transfer function and rename it to b, and we have new zeros in the system. You can see a 0 at minus 2.81 and a pole at minus 11.6. so what I'll do is that minus 2.81 a 0 and minus 11.6 a pole. We have this addition, and the final value of gain that we found out was, you remember, it was 254.4. okay, so I enter it, and now I open Sisotool of B to have a look that whether we have achieved the exact transfer function or no. You can see that this is the root locus of our new design system, and the poles are looking in a pretty good way, similar to the one that we have achieved in the previous task. Now I'll just click on the response to step command. Let's have a look. Okay, you just need to remove this green line first of all. Okay, so I'll click on characteristics of settling time and the peak response. So the calculations have worked out. It's 18% overshoot and exactly 1.99 seconds settling time. So this is the main crux of designing a lead compensator, or any other compensator or controller can be designed in the same way. It's just about the position of zeros and poles. You just need to set the requirements, as I've told you in this lecture, to the desired values, and then you need to make sure that the root locus is passing through these intersecting points, and after that you need to make sure that the closed loop poles are also passing through the desired this intersection point also. If they are not passing through these intersection points, I can show you that if we perform a response to step command analysis, I've opened a pretty much tabs, I guess. So if they are not passing through the intersection points, now if we perform analysis response to step command, let's see what happens. You can have a look that the settling time is 4.37 and the overshoot is 61.8 seconds of the new system that we have altered in the positions of the closed loop poles. So we'll make sure that these closed loop poles are passing through the intersection points. Okay, this is really important. And whether you design an open loop system, a PI controller, a PD controller, a lag compensator, a lead compensator, that doesn't matter. It's only in the location of poles and zeros that you place on the origin, left of the pole, left of the zero. It's only about the position of these poles. And also you can have a number of different combinations of lead compensators that you can design to have this requirement fulfilled. Even in this problem, you can see that I have changed the pole and the zero abruptly and just tried that the pole and that the root locus passes through this intersection point, and there can be a number of different alterations. I mean, we can have a number of different locations of sets of locations of this zero. you can see that I have changed the 0 location. Now I'll just zoom it out, and now I will change this pole location in such a way that it passes through the intersection point, and you can have a look that it has started to pass the intersection point again. See, and it's a newer combination of the 0 pole combination that we are using now. So there are infinite combinations of zeros and poles that we can have to design a lead compensator or a lag compensator, and in the similar way you can design PI controllers and PD controllers on your design problems or tasks using MATLAB. So this was the whole tutorial to guide you guys designing compensators using MATLAB. Inshallah, I will be uploading a new video about the same calculations using paperwork and handwritten calculations. So till then, take care of yourselves and do practice it at your homes, on your laptops, on your systems. Till then, Allah Hafiz, fi aman Allah.